a span to 2 years or 3 years, whereas one can argue that because of like things are moving so fast, why your program is of 4 years? I mean, why not it should be complete in 3 years? I mean, this can be interesting argument. Anyway, that is not part of the course or the discussion that we are interested to discuss here in this interaction. And please feel free to anytime unmute and ask any query or have some insight shared which you might be having in your mind. And then again mute. I mean, please, but just remember that you need to follow this simple protocol. Unmute and then say whatever you want to say and then mute again, right? So you know that computers are getting everywhere, this we discussed, and this computer science and engineering as a discipline, right? For quite some time, see, just when we'll discuss about the history, and you'll find it was very funny at times that to figure out that where we are heading to, and what should be the name of these new technologies or new developments which are going on. And there are so many nomenclatures that have come. And even if like at this point of time, the nomenclature has not settled, but though we can say in some sort like, yeah, computer science and engineering or computer science or computer engineering as typically are there like clear outcomes of the last 50 years of like development in computation science. Okay. So again, Pavan Kohli, Mr. Pavan Kohli, should I remember your name? I mean, this is, I have suggested something, but you people are still not behaving. I mean, see, if you don't want to attend, don't attend the class. That's fine. That's perfectly fine. Don't come to the class. But why you are there and you're not there? I mean, you're there and some sound is coming from you are also able to hear like others, and you're not responding. That means you're not here. I mean, there's a very straightforward conclusion one can draw, that you're just simply logged in and you're not here. So please keep this in mind, that if you want to attend this class, then be here. If you don't want to attend this class, not interested, just leave. Absolutely. Right. And yes. So CSE as a discipline, what computer science and engineering per se consider as a discipline, and there is a lot of debate which has run like almost 40 years and still on, that how CSE can be considered as a discipline, where as far as the our own discipline elements and engineering and systems are concerned, they are small considered to the application of computers in different domains. I mean, it can be like you're applying computers to solve problems in civil engineering, solving problems in mechanical engineering or electronics engineering domain. What about the problems of CSE itself, right? What are the problems of our domain? I mean, a discipline, to be a discipline per se, engineering discipline, that we should have our own problem, our own discipline problem, right? Just like mechanical engineering, they have their own problem of like creating this machines, right? Figuring out that what should be the material, the quality, the performance, right? And then the lubrication, the noise, and so there's lots of things like that goes into, and that is like mechanical engineering. Similarly, electronics also, like there's lots of different kind of circuits, and they perform some kind of like function mapping from some inputs to some output, and then these outputs can be fed to some other inputs. So you can have like very complicated circuits designed using electronics, and how this circuits gets into some kind of like this miniature chips. I mean, that is also like very interesting part, and that is part of like electronics. So you will see every discipline have their own set of problems, and big set of problems. They're a very large domain. What about computer science? And if yes, computer science is solving problem for everybody, But what about the problems of the computer science? And that we will discuss here. That it's not that we don't have problems. We have also like our problems, which we can consider as problems for our domain. Additionally, we solve problems of virtually all other domains. So you can consider that how critical and important this discipline is. When it not only it has its own set of problems, but it's also helping all other discipline to go to the next level and get those work done very quickly, very faster, and with less error. They will see that I will see some history of CSE. CSE typically a combination of computer science, which we will discuss that what is typical and pure computer science per se. When we say that different kind of discipline has their own science, own engineering. So what we do as a science and engineering in computer science, but I can tell you like that lots of interactions that we have with respect to other discipline also. For example, we are going to heavily interact with electronics engineering domain. Also will be like, for example, communication, which is like electronics and communication engineering. So you'll find that a lot of like data communication, information communication over wire or wireless. And that is also like we used to make use of that kind of like mechanism. And that's why that is our interaction with electronics. And not only like this, we design computers. And the computers are like typically have electronics parts. So this is again like this is like to quite a bit interaction between computer science and electronics engineering. Then we have interaction with very high like volume of interaction with mathematics as well as statistics. Even you will see that when we model problems, and a lot of mathematics models that we will be using to model problems in that sense and solving those problems using computers, like writing programs. And also like, for example, probability and statistics. So a lot of like our simulations and so modeling a problem and solving them and coming up with this, some inferencing, you'll find that we also going to make use of like statistics, a lot of statistics. And you know that the field like data science, machine learning, they make very heavy use of mathematics and statistics. And that is how like CSE in that sense like interact with this other domain. Then psychology and sociology. I mean, how come an engineering discipline or a science discipline? It's like natural, when we compare this science as a natural science. So how come like psychology and sociology can be like very much relevant and quite an interaction that is there between CSE and psychology and sociology? The point is that the problem that we solve is like are there in the problem domain, right? It can be from agriculture, it can be from avionics, it can be like let's say e-commerce or like communication, transportation, or whatever, like in some business, automation, so automobile. I mean, it can be, this problem can be any. But the thing is, our part that we try to solve, that is like software part or the hardware plus software, which is like hardware is like some embedded kind of systems, which is like maybe like you might be using an Arduino board or Raspberry Pi, and then you're using that to control certain devices, communicating with them, making use of Wi-Fi. So you will be writing some kind of software always, right? It's very unlikely that computer science or engineer people will only write, design hardware. They will, in fact, most of the time they are going to write software rather than they're going to design hardware. Hardware typically will be available, and we will be thinking of how to innovatively use this hardware, right? And this is how it is going to so mostly you're going to work for like software problems, right? Programming and software, designing software for that. So you'll find that this software, that is the kind of product that we have, this we can call as a product, right? Just like the products of other discipline, whether it's a building or it's some kind of machine or some kind of electronic chip. See, that's like physical product. Our product is a logical product, and that is to be designed and developed by humans, right? Now, we don't have, as of now, those kind of machines where we put on one side some material, some raw material, and get a finished product on the other side of the assembly. That we don't have like this kind of luxury or this kind of like stage, advanced stage that we have reached in this discipline. We are still like people are writing software, people are designing the software and then writing the software. So it's people skill that matters a lot, and that also is the recipe of that also like makes this a recipe of the success or the failure also. If you are skillful enough, if you understand the problem, if you can design suitably and implement with the other, obviously with the help of other people, then you will find that it will probably you are going to successful. Otherwise you will maybe you may not be successful also, right? I can tell you, like we have seen the failure rate of as I had 60% in 1960s and 70s when people were started writing software, and they were very costly software, and it was like very, very difficult to get them successful. So there are lots of money were getting wasted at the early stage of software development. So eventually there were lots of fact finding and lots of like, yeah, we have got research these issues that why developing software is a more difficult idea than actually designing and developing or manufacturing certain physical product. It's much more difficult, and why it is so, and so and so. Obviously, the two important component that has come is like this is like very complex problem, very, very complex problem. It requires lots of input from lots of domain when we solve a problem, and not only like we solve this problem, but we have to manage the changes which has to perform later on this solution. So problem is not that one time solved. Right? You buy a car which is like delivered to you, and now it is with you. It is not going to get modified in that sense, right? That is how, the way we modify software, right? We provide upgrades, and the car manufacturers, they don't provide upgrades kind of stuff, right? You see the straightforward difference, whereas we provide software upgrades. So our product is a different kind of product, and therefore, and most of like it depends on the humans, their skills. It's human leading this field, and therefore their interpersonal skills and their team skills becomes very important. So psychology of these people and sociology, how they behave in groups, that really makes a lot of difference between like the successfully solving problems or being unsuccessful at times. And since it requires a lot of like management, in the sense like people has to be managed, resources has to be managed, your project time, deadlines, right? A lot of like your customers. So you will find that it's not just like we are dealing with people. The kind of project is also that we get engaged in are more difficult kind of projects rather than those projects which are like typically building project or bridge project or some particular like physical product development project. The software projects are much more complex and more difficult to manage. So management is like as an important aspect of this discipline. We have to learn this management, even like this management skills, and you'll find since all these things makes this discipline a little more complex, little more involved, then you will see that this also like help people to be more smarter than other discipline people. And this is like I'm taking a pride to suggest. So it's not something which you go and challenge your like a peer in electronics or mechanical domain that you are going to be smarter than them. And this fact of the matter is like you are going to be, if you are going to acquire these kind of skills, definitely your thinking skills, your designing, planning, and executing those tasks, and you'll find that you're much better off with other people, other disciplines. There's something which is like, yeah, you can be happy at this point of time, but then yes, we have to develop this, and these will not come for free. That you have taken an update for computer science engineering and then you already got these skills. No, you have to acquire with a lot of effort, a lot of dedication, right? Commitment that you have to show that, and then once you have these skills, you'll see that why these people are leading the world is like because they can handle this kind of complexity. They can adapt to quickly to these situations also. So it's not that we develop or we write complex systems. We in solutions of the problem. So there are like there's like, for example, IoTs and sensors and deployment of the solutions to some areas, those kind of things. Like, it can be defense, it can be like in avionics also, like automobiles also. So our industries are going, and we are hopeful that in 5-10 years of time we will have a good manufacturing. And you should be happy that we have got like this institute as a manufacturing institute, where we would like to see that if we can augment this manufacturing with this smart devices, smart software, intelligent software, and probably we can lead the world again. Right. Let me give you a brief overview about like what computer science and engineering per se. I mean, we say computer science also, and then engineering also. I mean, it sounds like see, very hard. You see, it's not civil science engineering or mechanical science and engineering. We have got mechanical engineering, but then we have got this named like computer science and engineering, and this is somewhat unusual, and this is what you will understand gradually. But anyway, when we say that when science and engineering, that means there is a lot of science here also, part, component, and a lot of engineering that we are doing here. So when we'll discuss about the science, when we say science is like more of like theory of the computing. So it's about like theoretical computer science, which so a large domain of computer science, which is like particularly related with the computer science per se, where we know that what problem we can solve, what are the limitations, what kind of problem we categorize, we classify them. So we understand the nature of the problem, how we can solve these problems, right? So what is the theoretical limit? And can we do it better? So we can figure out these kind of things. Mayank Ingle. It's hard, right? Even like just we have 108 participants. There are not many participants regarding the size of the class, but still. But please mind that this course is going to be evaluated in terms of what we are discussing. So whatever we discuss and information we share, and we'll be asking questions based on this and related things, which I will provide some notes and to read or some articles to read about it. So that is what we are going to do for evaluating this course. Typically, after every four lecture, means a month time or maybe 3 lecture, we are going to have a quiz where this will be graded quiz. Right? So you tell this to your friends that yeah, this course is also a graded course where you will be appearing in a quiz kind of examination, and you're probably not going to solve any other thing just to appear in the course. So what is like theoretical computer science, and then this part which is like a sense of and the computer engineering and technology. So we'll see that this engineering is also have like this part technology, and there is some difference between engineering and then the technology. So sometimes there are some degree which are being awarded at computer science and technology, or computer technology, or computer engineering. So it's not that they are same, but it's not that they are entirely different. There are quite a bit overlap, but we will understood that what is the difference between when we say computer engineering or computer technology. So that is the core part of our domain, where we are like got the tools, techniques to solve problems, and then we are applying these tools, techniques to solve problems in the various domains. So we got this computer applications here, right? So this is like it can be like a slide which I got from internet, and I've got this resource which is going to be shared with you, and it can be like quite a crowdy, but don't worry about it. Like what you can do is like we can first take a look on. So theoretical computer science. So what part makes this this computer science as theoretical computer science? So what is the elements of theory in this domain, right? So it started with like this Turing machine. So it's like a Turing machine is typically a model for today's computer, but then it started with when Alan Turing, the name of the scientist, like which is called father of computing, right, proposed this machine in around 1945 and so. And this machine was like a kind of reading some in symbols from a long tab, which can be considered as infinite long tab. So you're never running out of the memory. And that can be considered as closed because we have got much huge memory which we can use to store programs and read from them and perform some job. So this is like the infinite tab where there were symbols in the form of zeros and one, right? And then this tab can be moved from left or right. And where is the tab? So there is some kind of information about the state of the tape, which can be stored in this register, which is like a state register, which will figure out that where we are, so that if we are in some state and we read something, then we do some, we can take some actions and go to some other state. So it's like more of like it's making transition from one state to another state. And there were like a set of instructions written, right? So these instructions will be asking to like do some jobs, right? So it may be read from the tab or write to the tab. So those kind of things or move the tab left or move the tab right. So these are the like basic building blocks of this, like the proposed computer at that point of time. And I can tell you that not this effort, but there were other efforts also to design computer. And they were all eventually figured out that they were of the same model, though they might have used different terminology, different visuals, but then essentially they said the same thing, that we are going to have like infinite tab, infinite like stream where the input may come, or you can produce input which may be written on that back on the tab, or you may have two tabs. One, you're taking one from for input and another one for writing output. And then there are some instructions which are like to be given to this computer about like moving this tab left or right, or writing it something or reading from that positions. And while we do it, the machine knows that where machine is, like there's like which state the machine is. So it becomes like more of like deterministic kind of thing, that we know that where we are and what we are doing, what we have read, instruction and what instruction we are supposed to do, and then produce some output also, right? So those kind of things. So this is basically a model of Turing machine, the name after Alan Turing. And I can tell you now this we have this like award which is called Turing Award, that we give every year to the pioneers in the computing field. And I can tell you there is no Nobel Prize in computer science, because you know that Nobel are given in like 4 or 5 domains, and that's what I mean traditionally has been. But then I can tell you like Turing Award is considered as the like most respected award in computer science. Right? It's the highest award a person can get who is working, who is a IT person or computer science person, and whose contribution in the area of computer science. So that's just a like model was created, and then like people have started grouping these instructions and figuring out that what can be done with this computer. So can you like represent those problems in the form of like some instructions, and can this instruction together can solve bigger problems? So eventually it has been realized that yes, though machines does very elementary tasks, it's simply like moving these tabs, reading from the tabs or writing on the tabs, right? And performing very elementary operation like adding, or I mean, all this like can be converted adding, subtractions, increment operations. So for very basic operation and making a jump from one instruction to another instruction, so you can have a control flow within the program. But writing this kind of program can allow you to like do some task and gradually, because there is no limit to like how much you can write, so you can make it more complex. You can write a lot of, and then you can start making them this program, this small chunk of instruction into some kind of groups, some kind of functions, some modules, and can then reuse them in some other code, right? So this is gradually they started figuring out that you can build a lot, I mean, more complex computation out of this very simple idea of these simple instructions. And given like in this infinite memory, you can write the biggest program, right? And they can eventually do anything. I mean, anything in the sense like very complex things, right? And we'll see that what things they can. So then people started to figure out that what are the things that can be done by a computer. So what can be computable? What can be solved using computer, or what cannot be solved by the computers? So again, like this is an area become like, which is called computational computability and complexity. Those are like computational complexity or computability and complexity, where what we do is like we figure out, can we solve a problem? So we, let's say, given a problem, can we do it by computer? The question is this. Now we have to figure out that what kind of problem it is. Is it like a problem which falls under some class or another class or third class? So we got this problem classification based on the like complexity of the computation that are involved, right? And that's what it is called. This area, this whole area is called computational complexity, where we have this famous problem which is still not solved. What it says that whether P is equal to NP. Now what is P? The problems which can be solved in polynomial time. Now this might sound a little weird for now, for all of you probably, or most of you who are new to this computer science. See, when we are solving this problem, that means we are writing the steps of this problem, and we are writing some kind of algorithm, right? And you know that this is like, here is this algorithm term, that we write everything in its steps, right? Whatever we want to achieve, we make use of these like simple statements, and we write them in some steps. Maybe there can be some decision statements or some kind of looping. And probably in this course, while you are going through in your computer programming course, you will figure out that any task which computer can solve can be modeled using 3 sets of instructions, right? There can be many of them, but then these are essentially 3 types of. One is assignment statement. The second one is like decision statements, which is like if or switch statement in C, or like you know that. And then we have loop construct. So these 3 types of statements will allow to write a recipe of solving a problem, right? So this we can do. I mean, this is when a problem can be solved by writing program. If we cannot write we cannot solve a program, that means we cannot come up with an algorithm. That means we cannot have an algorithm where we can have these 3 types of statements written in some order, and they together can solve this problem. I mean, it's not possible. Then there's 2 things. It's not possible. So like showing it, establishing it that we cannot do it is one thing. The second thing is, it may be possible, but as of now, we don't have a solution here. So as of now, none of us knows about like how to, but then we neither have a proof that it cannot be solved. So you see, like we got this kind of quite some time we got this kind of argument that what problems can be solved by computers, what problems cannot be solved by computers. And while these arguments were made and analyzed, we also figured out that there are ways of solving problem efficiently, and there are ways of solving problem not so efficiently. And that's why we got this idea of P, which stands for polynomial time. So I'm not going to discuss this for today, but in some other lecture we'll probably brief about like what is P and NP. But when we say P is like polynomial time, that means it's a measure of the computing time, which is efficient, which is typically considered as efficient. P is polynomial. So if we say that if some algorithm is of time complexity as let's say n, order of n, or order of n square, or order of n cube. So n cube, n4, these are nothing but the polynomials of degree of n, right? And what is n here? The input size. So what input we are taking, and then based on the size of the more input you take, the more processing will be required probably. And that's why this computation time or the computing complexity is measured in terms of input size. And if we can come up with a formula, come up with a like expression where the time taken by can be expressed in terms of input size, whether it's like of the order of n, of the order of n square, n cube, or some more complex expression, n cube log n, or whatever like it can be. So that is nothing but this gives us a kind of understanding that how efficient is the solution, the algorithm that you design. And that also allows you to compare across algorithms. Can you come up with a better algorithm? Can we prove that there is some kind of lower bound that there cannot be any algorithm which will take less than this much of time? Time not in millisecond, but time in terms of like some like complexity notations, and that you will understand eventually. So this becomes like a very big part of like theoretical computer science, that whether a given problem can be solved or not, and if it can be solved, then how much, what is the complexity of solution? I mean, whether this complexity is simple, which is like P, whether the solution is P in P, polynomial time, or it is not in polynomial time. NP stands for non-deterministic polynomial, right? We'll discuss that sometime later, but then I can tell you that as even at this point of time, if you look at the problems that we try to solve across the globe, the whole world, like using computers, you'll find that very small subset of these problems are like key problems, very small subset. You can say almost insignificant portion, which is like we can solve in P. The real problems are actually hard problem, which we call as NP hard or NP complete. Again, these are some terminology, but then don't worry about at this point of time. Just assume this, that we don't have efficient solution for these problems. And what does it mean by we don't have an efficient solution? That means we can solve this problem. The problem is that as the input size increases, let's say we can solve it for n equal to 10. We take 10 numbers and we process them and provide some solution. If we take like 100 number, obviously processing time will be more and will take some time and get the output. If we take 1,000 number, so as the n is increasing, as the input is increasing, the processing time in some sense is exponentially increasing, right? If the nature of the solution is like this, that when it takes exponential amount of time compared to the input size, then these are considered as hard problem, because you can solve this problem in finite time, in reasonable time for a small size inputs, but as the input is growing, it's taking a lot of time. And I can tell you, like, you will be told about some problems, very simple problems, sounds to be extremely simple, but when you write some algorithm for them and use some algorithm to solve them, that algorithm can take the whole life of universe, and the algorithm is not going to finish. So that is something which is very interesting and very useful in thinking about like how we solve problems, how good we are in solving some kind of problems, and can we figure out upfront that given a problem, can we solve it in an efficient way, or we don't have an efficient solution just now. If we don't have efficient solution, can we I mean, it's progress and name and fame, that even if it is a difficult problem, even we don't have a deterministic polynomial time algorithm, we can apply certain traits and way around and still can make use of computers to solve that problem. Here the compromise is that the solution may not always be right, but maybe in 90% of cases it will be right, or it will be optimum. So we may not be able to give a guarantee that this is the best solution, but for humans, since human can also satisfy with less than ideal also. I mean, that's a realistic situation. What they want is quick solution, and even if it is slightly less quality or that, they may compromise a little, given that the optimum solution may take all of your money. So you can you're not going to give you all of your money. You will say that, okay, you take this reasonable money and give me a reasonable solution. I'm happy. And that is how we have become quite successful in solving all those hard problems also, which are very hard in principle to get it solved in the best possible way, optimally. But what we do is we know, if we know that we cannot solve them with our know-how at this point of time in the most optimal way, in the finite time and finite resources, then we can use some approximation algorithm or some kind of heuristic algorithm which can help to solve this problem in a suboptimal way, but very fast. And probably it's whatever you invest is more return that you get, because your investment are small compared to the kind of solution that you get. So these are this form the part of computational complexity of theoretical computer science. Then we have algorithms. Then we compare this algorithm across. You'll see that there will be some fundamentally important algorithms, just like you have a set of data, you want to figure out if some element is already there, or you want to search within that data. It can be used data also, it can be small data. Generally we work in large, right? And whether you're interested to know whether some customer details are there in that data or not there, right? So you're searching the data. So searching in a collection of data, large collection of data, or sorting in data in some sense, to perform some kind of other operations which can be based on sort, right? Those kind of things. So you will find that sorting and searching are very fairly standard algorithms, and typically there are many algorithms, many alternatives, many candidates for performing sorting and searching, and then we can figure out that how good they are in general or in a specific situation. One is better than other. Why? So this is how they allow us to understand the nature of computation, nature of how do we write instructions, how do we solve these programs, how do we solve the sorting programs, how do a sorting problem, how do we provide solution for searching problem. And that will tell you that when you go and solve some problem other than searching and sorting also, then what general understanding that you have to have, and what things can be useful. So this part is nothing but forms theoretical computer science. There is some more elements also, for example, computational geometry. There's complex geometry out there, and you want to figure out that. I believe that you are familiar with geometrical figures and geometrical calculations. It's it can be more complex. It can be done in high dimensional space, and we can actually come up with figuring out that can we compute the property of this particular geometry, or evaluate this angle, or find the side of this, or find the enclosing box of this complex figure, three-dimensional figure, or so and so forth. And similarly, we have got this graph theory, which is very useful tool, because there's lots of problem can be modeled as graph. You'll understand, and I'm going to give you a lot of examples about which can be modeled as a graph. It can be directed, it can be undirected, and then after this modeling is nothing but solving some property or computing some property of this graph, and that is nothing but when we get this property, and we can take it and map it to the problem and get a solution of that problem. So this modeling, the graph theory, computational complexity theory, and this automata theory, you'll understand, and the quantum computation nowadays, like this is also like getting into a lot of like news that the new age computers, new computers that are going to be even more powerful, and which will ignore this problem of P is not being NP. Even the hard problem can be solved the most optimum way, because these quantum computers are going to be very, very fast. I mean, 100 or maybe million times faster than the traditional computers. So still, like a lot of research is going on in computer in quantum computing, and then there is some research like theoretical area where you how you design a programming language. So, and what is the capability of programming language? What can they do and what they cannot do? So you'll find that it's more of like a lambda calculus, that is like a mathematical structure that we make use of to model the capability of computations and express them in those statements of like lambda calculus. So you'll see that there is a very close association between programming languages and lambda calculus, and this is you'll see that these programming languages are inspired by this kind of processing, lambda calculus, and therefore a lot of computation that we do is like very close. So if you are interested to design a new programming language, again, this is a slightly theoretical aspect of like how we are going to have those kind of statements or syntax, and so the capability of programming language and analyzing the properties of programs, this is all like that falls under this theoretical computer science, right? So let's, I think, stop here. We'll think, what is the time? Yes. And what we have done is we have taken a look on theoretical aspect, I mean, theory part of computer science, and what makes the theory of computer science, right? There is like information theory also, like cryptography, where like information, as you know, that data is stored in form of bits, binary digits, right? 0 and 1s. And then if you store some, let's say, image of a flower somewhere, right? So you know that there is a file named .jpg, and if you open this file in some notepad, you will get some garbage. It's nothing but like some code on which using which this information is coded that you see. And if you can open this in some kind of image processing software, image opening software, then this will look like an image, right? So how this image, like this information, can be compressed further, right? So like compression, porting from one, converting from one form to another form, right? So not only just images, like it can be text also, and you might be interested to hide text or do some kind of cryptography. So you know this information theory and the cryptography, they are very much related to the way we deal with information as a computer scientist. So how do we store the information? How do we process them? How we make this information like accessible or not so accessible, or code them, compress them, uncompress them, like those kind of like idea that again like come in this theoretical part of information theory and cryptography. And we have some course to offer where you will learn about information cryptography and information security, and also for computability theory and algorithms, which will also include this computational complexity stuff. So we are fairly going to cover this part in our curriculum. And then now we are going to discuss it. Next time we'll discuss about the engineering and technology part of computers. If you have any question, please ask. Yes, please.
सब ब्लॉकचेन जो है वो इन सब में से किसका पार्ट होता है?
वो क्रिप्टोग्राफी और उस एरिया में आएगा, like security part में. So how we can have like these cryptic currencies, and then transactions we can make more secure. So those kind of things. Yeah, so these are the latest development in this field, and that's why you can see like this field is very dynamic, and that is an application part of, like, you can say, cryptography and yeah, information theory that you will be applying to, like, solve these real problems.
So
Okay,
what
sir.
is the basic functionality of blockchain systems?
Blockchain system, see, I think let's not go there, because that's quite an advanced area. We are just introducing you with profession, so it may make you a little confused at this point.
Okay, sir.
So what we do is, like, we'll have some look on that, and then I'm also, like, planning to bring my faculty in different domain to interact with you, who are, like, expert of different area, right? So they will tell you, like, more detail about, like, slightly more detail. We are not going to get into like absolutely, like, in that hardcore theory or problem solving in that particular area, but then it will give you the idea, the applications, right? The kind of things happening and the important things which you should be focusing. If you want to start now, so what you should be doing. So those kind of information and insights will be helpful to you, definitely. Yeah. Okay. So if there are no more questions, then should we stop?
Yes, sir.
Okay, sir.
Okay, so thank you very much, and encourage all of us, I mean, all of your friends also. It's like going to be somewhat informal discussion where we try to understand everything, not just the curriculum. I'm not just telling you the curriculum. What I'm saying is, like, this whole field where lots of happening in everywhere. So we'll try to cover as much as we can to have a good understanding of this profession, not just curriculum that we are going to, and how this curriculum is going to help, like, in this profession, how it is helping, so you can connect the kind of courses, the kind of skills that will be required to, like, opt for a profession. So how you should be actually focusing your effort more on particular courses or skills that might be more useful to you because of that reason. Okay. Okay. Bye. See you then.
Thank you,
Thank you,
sir.
sir.
Thank
Thank you,
you.
sir.
Thank you, sir.
Thank you, sir.
Thank you.